Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Welcome back. Problem 8.3. The statement of problem is an overhanging W920 by 449 rolled steel beam supports a load P as shown. So you can see this is an overhanging beam and it supports load P at point C. P is equal to 700 kilonewton. This A distance is 2.5 and allowable stress is 100 megapascal. So you have to determine the maximum value of normal stress sigma m in the beam. Part B is maximum value of principal stresses at the junction of flange and web, and see whether the specified shape is acceptable or not. So let's start with the given data. So it is given that W920 by 449 rolled steel beam P is given as 700 kilonewton, so it will be 700 multiplied by 10 raised to power 3 Newton. Clear? A is given as 2.5 meter and sigma allowable is given as 100 megapascal. So what you have to do is to find in part A, it is given to find the maximum stress in the beam. Clear? In beam. Clear? Or normal stress. In part B, you have to find the principal stresses. That is, you know, this is maximum stress, principal stress. That is sigma 1 at the junction of web and flange. And from problem 8.1 to 8.2, now you know what is web and flange. So the junction of web and flange is the portion where this web meets with this flange. Clear? So you have to find the principal stresses at this junction. Clear? And in C part, to check the shape is acceptable or not, or the beam is acceptable or not. So let's start with the solution. Clear? So for first, in order to solve this problem, you will have to find the unknown reaction forces at point A and B. So for that we will draw the free body diagram of this beam. So this is the free body diagram. This is point A. So here the force will acting as at point B. There will be a force acting upward. This will be RB. This is point B. Clear? And at point C, this will acting downward P. So this force will be again. This will be also downward. Clear? And this will be RA. So by using equilibrium condition, you will apply sum of all forces along y direction is equal to 0 and upward force is taken as positive. So you can see RA is downward, so it will be minus RA plus RB minus P will be equal to 0. So it means that RB minus RA is equal to P. So this is one of the equation that we get from the equilibrium condition. This is equation number 1. Now we will apply sum of all moments about any point is equal to 0. So you can decide the point. You can take it point A or B or this point C as well. Clear? So if I am going to take the moment about point A is equal to 0. So you can see that force that is producing moment is RB. So RB into perpendicular distance, this distance is given as A. Clear? You can check it. This is A. So RB into A is this is counterclockwise, so it will be plus. The second force which is producing movement about point A is P, and this is producing clockwise, so it will be minus P into perpendicular distance is, this is A and this is A, so it will be 2A. So P into 2A is equal to 0. It means that RB into A is equal to P into 2A. Again, A will cancel with this, so RB will be equal to 2 times of P. Now you have this equation is second. You can put 2 in 1. You can put 2 in 1. When you put 2 in 1, so this will be equal to 2P minus RA is equal to P. So implies that RA will equal to P. So now you have the value of RA and RB, as well as we will move further. In part A, it was given that to find the maximum stress in the beam, and we know that maximum stress in the beam is equal to maximum bending moment divided by section modulus. Clear? So for maximum bending moment, we will draw the shear force and bending moment diagram of this beam. Let me draw it. So let this is the beam. Clear? This is RA, which is given as P. Clear? RB is at the mid, which is equal to 2P. Clear? And this is P. This distance is equal to A, and this distance is also equal to A. So for shear force, I will draw vertical lines. Clear? And draw the shear force. So this is point 0. Now you can see at point A, this is A, this is point B, and this is point C. So at point A, the only force acting is P, and P is equal to, it is given P is equal to 700 kilonewton. So let this is in kilonewton. So let this point is, P is negative downward, so minus 700. Let this point is minus 700 kilonewton. And you when you draw it, you will draw it as per scale. Clear? So from point A to B, this 700 will remain the same. But at point B, you can see this is, now there is 2P, which is minus 700, 2P is 1400. So minus 700 will come, bring it to 0, and plus 700. So this will be like this. And again from B to C, there is no force, so it will be same. Clear? So this is shear force diagram. This point will be plus 700. So from here you can get maximum mod of maximum shear force is equal to 700 kilonewton. Okay, now we will move toward and we will draw the bending moment diagram. So bending moment diagram of this will be like, for example, if this is axis or this is bending moment, and bending moment will be in Newton into meter. Okay, and you know that this was point A, this was point B, and this was point C. So the area under the point AB is shear force diagram. This is the shear force diagram for A and B. So area under this AB will give you the bending moment, and you can find the bending moment by multiplying this. Since this is rectangle, clear, so area of rectangle is 700 multiplied by A, and this A is also given as 2.5. So when you multiply 700 with 2.5, so you will get minus 1.75 into 10 raised to power. It will be when minus 700 multiplied by 2.5. Clear? And this minus 700 is in kilonewton. So when you multiply this, so you will get minus 1.75 into 10 raised to power 6 Newton into meter. So this is 10 raised to power 6 Newton into meter. So look, you have to locate minus 1.75. Let this point is minus 1.75 into 10 raised to power 6. Clear? So you can see at point B this the area of under this will be minus 1.75 into 10 raised to power 6. So at point B the movement will be this one. You can see this line is a straight line, a 0-degree line, so bending moment will be the linear line, and since it is negative, so slope will be downward. So this will be your bending moment between point A and B. Similarly, from B to C, again you can see this is the area and this is same 700 multiplied by this A distance, which is 2.5, and it will again give you plus 1.75. So minus 1.75 plus 1.75 will give you 0. And since this is a 0-degree line, so again it will be and positive, so your slope will be upward and it will goes to 0. So you can see the maximum bending moment is equal to 1.75 into 10 raised to power 6 Newton into meter, and this is 700 into 10 raised to power 3 Newton. Now we will move toward finding section modulus, and as it is given that this is beam W 920 by 449 rolled steel. So if you go to the appendix C of the book of mechanics of material, you have to take all the properties, that is depth of the beam, breadth of the beam, breadth of the flange, thickness of the flange, thickness of the web, second moment of inertia, section modulus. So you will have to note them and you will write them again. So I have written their values. D, our total height of the beam is 947 millimeter. Clear? Breadth of flange is equal to 424 millimeter. Thickness of flange is again given as 42.7 millimeter. Clear? T, thickness of web is given as 24 millimeter. I, second moment of inertia about x-axis is given as 8780 into 10 raised to power 6 mm4, and section modulus Sx is given as 18,500 into 10 raised to power 3 millimeter cube. Now you have this value, you can put it in this formula, that is maximum stress, bending stress is equal to moment, and this moment is 1.75 into 10 raised to power 6 Newton meter divided by section modulus, which is 18,500 into 10 raised to power. This is in millimeter, so if you convert it into meter, it will be 10 raised to power minus 6. Okay, so 1800 into 10 raised to power minus 6, and it will give you 94.59 megapascal. So sigma max will be equal to 94.6 megapascal. Now this was part first of the question 8.3. This is the answer. Now we will move toward part B. So in part B, it was given, it was asked to find the principal stresses at the principal stress at junction of flange and web. So again, if you draw the flange and beam web, so this is, let's say, flange, clear, this is web, So total height is D. From this point till this point, it is D. And if you divide D by 2, so that will give you centroidal axis. So this distance will be C, and this C will be equal to D divided by 2. And when you put the value of D is 947 divided by 2 will give you 473.5 millimeter. Clear? Now this is the distance from neutral axis to topmost surface. Now we will find this value, and this value is YB. Clear? Because this is a junction between flange and web, and this distance will be equal to, this YB will be equal to C minus T of flange. This is TF. This distance is TF. And TF is also given as 42.7. So 473.5 minus 42.7 will yield you YB, and this YB is equal to 430.8 millimeter. So now for finding the stress at this junction, let this is point B, and we are interested to find out the normal stress at this junction, which is sigma B. So this sigma B will be equal to YB over C into sigma max. Clear? So this YB is 430.8 divided by C is 473.5 into 96.6 megapascal. So this sigma B will be, when you calculate it, this sigma B will be equal to 86.04 megapascal. So you can see the stress is reduced because the maximum stress will be at the outer surface of the beam. Clear? Now you have this sigma B, and again for finding principal stresses we have normal stress at this point, but we do not have shear stress tau of xy. So for tau of xy we will calculate the shear force. So shear force, as we know that this is equal to V max into Q divided by I into thickness of web. We have V max from the shear force diagram. I will show you. We have V max. Clear? We have I, that is given as second moment of inertia. We have thickness of web. We do not have Q, and this Q is equal to area of flange into YF dash. Now what is AF? So AF is equal to area of flange is equal to breadth of flange multiplied by thickness of flange. So PF into TF. So you have both the value. When you multiply both the values, so it will give you 86.1 into 10 to the power minus 3 minus 6 cubic meter. Clear? Now for finding YF can be easily find out by using this formula, that is equal to 1 over 2 C plus YB. Now you can see this is C, and from neutral axis to outermost surface this is C, and this is distance YB. Clear? So their sum divided by 2 will give you a point which is known as YF. So let's say this will be your YF. YF dash. Clear? So you have C value 1 over 2. C is equal to 473.5 and YB is 430.8. Clear? 0.8. So you can calculate this YF dash will be equal to, I have over here calculated 452.1 15 millimeter. Now you have AF and YF. You can multiply it, and I will simply write that last one will be equal to this will be 86.1 into 10 raised to power minus 6 cubic meter. One correction you must do it, that this area is not equal to this. Clear? So when you multiply BF with BF is this 424 millimeter and TF is 42.7. So when you multiply them, it will give you 18.10 into 10 raised to power 10 into 10 raised to power 3. 10 raised to power 3 millimeter square. So you have to be very careful. Okay, so now you have Q, you can put it in this formula. So shear force maximum or tau xy will be equal to shear force, and shear force was 700 or 700. Let me show you. 700 into 10 raised to power 3 Newton. So 700 into 10 raised to power 3 clear, multiply by this Q, which is equal to 81.86 8186.1 into 10 raised to power minus 6 clear, divide by I of the beam, which is given over here, that is 8780 into 10 raised to power 6 millimeter 4. So it is 8780 into 10 raised to power minus 6 into thickness of web is equal to 24 millimeter. So you have to convert it into meter. So it will be, this I is also in meter power 4. So when you calculate this, tau xy will be 27.19 megapascal. Now you have normal stress as well as shearing stress. So you can put the in sigma 1 is equal to sigma average plus R, and we know that sigma average is here. Only there is normal stress sigma B. So sigma B divided by 2 plus R is equal to sigma B divided by 2 whole square plus tau xy whole square. You have the value of sigma B. Sigma B is equal to 86.06 divided by 2 plus minus, sorry, not minus, because we are going to find the maximum normal stress. So 86.06 divided by 2 whole square, and tau xy is 27.19 square. This is normal stress or principal stress. Clear? So when you calculate this, principal stress will comes out to be 93.9 megapascal. So this is the answer of part B, that is to find out the principal stresses at the junction of flange and web. The third part is to check whether this is acceptable or not. So for that, what we have to check that this principal stresses at the junction of flange and web should be less than sigma allowable. So again, this is sigma 1 is 93.9 megapascal, and sigma it should be less than allowables, and sigma allowable here you can see this is 100 megapascal. So Again, this is less than 100 megapascal. So conclusion is that W 920 by 449 is acceptable. I hope you have learned from this video. Thank you for watching the video and supporting me. Take care.